Script: Causal inference with counterfactual reasoning in temporal graph neural networks for dynamic systems. Imagine you're planning a road trip and wondering, if I had left just 10 minutes earlier, would I have avoided that traffic jam? This everyday curiosity is at the heart of a powerful idea in science and AI, causal inference, asking not just what happened, but why, and what might have happened under different circumstances. Today, I'm going to take you on a journey through how modern machine learning tackles these what-if questions inside ever-changing, interconnected systems, using tools called temporal graph neural networks with counterfactual reasoning. First, let's break down what all that means. Picture a vast, bustling city where intersections are constantly changing, streets get blocked, new roads open, sometimes accidents create ripple effects through the traffic network. In science and business, we often deal with similar kinds of dynamic systems: social networks with friendships forming and dissolving, financial markets with money flowing between accounts, power grids or supply chains, or even patient records in hospitals as conditions change over time. In all these cases, the relationships between entities, like people, places, devices, shift with time, forming what's called a temporal graph, a network that's constantly evolving. Machine learning models called graph neural networks, or GNNs, are especially skilled at learning from these types of networks. GNNs essentially teach themselves how information or effects ripple through connections. But when you add the dimension of time, asking not just who influences whom, but when, and how does that change, you get temporal graph neural networks, TGNNs. These are like supercharged navigation apps, constantly updating themselves not just on the fixed layout of the city, but also on the surges and drops in traffic hour by hour. But even TGNNs typically focus on predicting what will likely happen next, given what we've seen so far. The real challenge arises when you want to ask even deeper questions: why did something happen? And what could have happened if things played out differently? That's where causal inference and counterfactual reasoning come in. Causal inference is a bit like being a detective. It's about understanding the chain of cause and effect, not just spotting correlations or patterns. For example, let's say you notice that a particular factory shutting down often leads to a spike in citywide power outages. Is it a coincidence, or is the closure actually causing the spike? Standard machine learning might just notice the pattern, but causal inference wants to really test it, ideally even run an imaginary experiment. If the factory hadn't closed, would the blackout have still happened? Counterfactual reasoning gives us the tools to simulate these alternate realities. The word counterfactual simply means against the facts. It's asking, what if the facts were different? In our travel analogy, you might wonder, if I'd taken a detour, would I have been on time? In AI, this means building models that can estimate what would have happened under different interventions or scenarios. Now, let's see how all this comes together in practice. Suppose we're running a smart electricity grid. We want to decide if upgrading a particular substation will actually prevent blackouts elsewhere. By representing substations and power lines as nodes and edges in a temporal graph, and feeding historical and real-time data into a TGNN, our model can learn how failures propagate. But to make causal decisions, we don't just want to predict future blackouts, we want to estimate what would have happened under different upgrade strategies. Counterfactual reasoning lets us do this. We can simulate the network's behavior, asking, if substation X had received an upgrade last winter, would last summer's outage in District Y have happened? Another example is social media. Imagine trying to understand the effect of a new policy, say, banning certain types of content, on the speed and shape of misinformation spread. A TGNN can model the evolving friendships and message flow over time. Using causal inference, you can estimate, if we hadn't introduced this policy, how different would the spread have been? One more scenario: consider drug discovery in medicine. Patients interact with one another and with the healthcare system over time. New drugs come on the market, protocols change, patient groups form and dissolve. A model using causal counterfactuals and TGNNs could help estimate not just which treatment worked in the past, but for patients with different connections, at different points in their illness, would this other treatment have led to a better recovery? Why does this matter? First, it helps us move from mere prediction to reliable decision-making. Knowing what might happen isn't enough. Leaders and researchers want to know why, and how to change things for the better. Causal TGNNs with counterfactual reasoning can inform policy, proactively prevent disasters, and personalize interventions. They help us avoid drawing the wrong conclusions from coincidence and allow for much safer virtual testing, where real-world trials might be dangerous, expensive, or unethical. Some common questions might be, is this just replacing human experts? Not at all. Instead, these tools empower experts by giving them evidence about alternative scenarios. They become more like co-pilots than pilots. Another likely question, is this technology found in systems like ChatGPT? While ChatGPT doesn't directly use temporal graph neural networks, the underlying concepts of learning from data, understanding context, and eventually thinking about counterfactuals are a growing frontier in all advanced AI systems. To wrap up, causal inference with counterfactual reasoning inside temporal graph neural networks is opening a new chapter in machine learning where we go beyond passive observation to active, thoughtful simulation.